right, welcome back. We are going to now work through problems 11 through 14 from Thursday's homework. So the solving trig equations. So these four problems were a little bit different. So I know we solved number 11 together in first block. We solved number 12 together in third block. So I'm just going to start at the beginning. So feel free to fast forward or skip ahead or around to whatever you want to see, okay? So 11 and 12 had similar characteristics in that they both required us to rely on the Pythagorean identity. So the Pythagorean identity, we all know, we learned it in our last unit, but it's the cosine squared plus the sine squared is equal to 1. Obviously, order doesn't matter here when we're adding, right? It's commutative. So in this situation, the reason we have to use this identity is because we solved previous problems that were squared, right? And then we were able to use factoring to help us, but in order to factor, we would need to have the same trig function to factor using quadratics, right? The other method of factoring GCF, even still, we don't have a GCF if we have a sine and a cosine. So that's why we're going to rely on the Pythagorean identity. So it's just a little trick that we can use to make our lives a little bit easier. So for this problem in number 11, I want to swap out cosine squared using the Pythagorean identity. So I'm going to solve the Pythagorean identity for cosine squared. Sometimes we solve it for sine squared. It just depends. It just depends on the problem. So I'm subtracting sine squared to both sides. I get the cosine squared equals 1 minus the sine squared of theta. And I don't have to do anything else. Again, I'm just using this as a stand-in. If I want to go and replace cosine squared, right, I'm going to replace it with what I've just set it equal to. So the left side becomes 1 minus sine squared of theta equals 2 plus 2 sine of theta. And now we have an equation that's only in terms of sine, and that's great. That's going to be very useful. So now we can combine like terms, set this equal to 0, and then factor it as if it was a plain old quadratic equation, right? So you guys know my preference. I'm moving everything to the left. So it would be 0 equals sine squared of theta, because it turns positive, plus 2 sine of theta. So I'm just placing these in order. I'm subtracting 1 from 2, so I get plus 1. So now it's nice and easy, right? We had something that was a little more difficult. We used Pythagorean identity. We have sine squared plus 2 sine plus 1. So A is equal to 1, B is equal to 2, and C is equal to 1. So when we factor this, we're looking for two magic numbers that multiply to give us 1 and add to give us 2. Well, that's pretty easy. It's 1 and 1. So I can set this up. I'm not using x like I would if it was a quadratic. I'm using sine of theta. That's our variable. So sine of theta plus 1 times sine of theta plus 1. Now again, I could check my factors to make sure I did this correctly by distributing, otherwise known sometimes as FOIL, sine times sine, sine squared. Sine times 1 is sine. 1 times sine is sine. That's where the two sines are coming from. And then finally, 1 times 1 is 1. So that's what we're doing. We're just rewriting that equation. And the reason we factor is to use zero product property. So sine of theta plus 1 equals 0. I take each factor and set it equal to 0. These factors are identical, so I don't have to do that twice, right? This is the same equation. No matter which way I solve it, it's going to give me the same answers. So this tells me the sine of theta equals -1. So theta is the arcsine of -1. We know what this means. One angle on the unit circle has a y-coordinate equal to -1. So where does that happen? Where's the y -1? Down at 3 pi over 2. And here's our answer. Easy peasy. All right, number 12 is similar. We have sine squared of theta plus 2 minus cosine squared of theta equals 3 sine of theta. Again, I'm in a scenario where I've got cosine, sine, And both of those are squared. We have a constant and we have a sine. So we have a mixture of trig functions. And the only way we could just jump straight into factoring right now is if there was a GCF, because I can't factor a quadratic with two different variables. And by variable, what I'm including here is just the trig function, so sine and cosine. So I have to do something different. I've got to approach this one differently. So again, we're going to use the Pythagorean identity. But you have to think about which squared function you want to substitute in or substitute out or whatever works for you, whatever wording works for you. So I'm going to choose to substitute in cosine squared because I have two sines already. So the cosine squared is the problem. He's the problem child. So let's get rid of him. So just like in number 1, where we substituted in 1 minus sine squared for cosine squared, we're going to do that right here. This one's a little tricky though because there's a subtraction sign in front of it. So because I'm subtracting two terms now instead of one term, I have to make sure to distribute that subtraction sign. So let me show you. Keeping the first term, keeping the second term, I'm subtracting. I'm turning cosine squared into two terms, 1 minus sine squared, just by manipulating the Pythagorean identity. That still has to equal 3 sine of squared. So I'm not changing any values in the equation. All I'm doing is rewriting it in a way that makes my job, which is solving it, easier. So I have to subtract both of these terms. That's why I include the parentheses here. You should do that too, so that you don't neglect the second term. That's the most common error. Subtract 1 and subtract negative sine squared. So here I go. Sine squared of theta plus 2 minus 1 minus negative sine squared. So I'm adding sine squared. That's important. If you missed that step and you left it negative, you would cancel this guy out, and then you wouldn't get all of your solutions. All right, equals 3 sine of theta. And now I'm in a much better position. This is a type of problem that we would normally see. We have sine squared, a sine, and a constant. This is going to be very similar to number 1. I'm going to start by combining like terms. Sine squared and sine squared together make 2 sine squareds. Okay, I'm just going to cross them off so we can keep track of what we've done. This this 3 sine of theta needs to move to the other side. I'm going to make it negative 3 sine of theta. I subtracted it so it would cancel over here. And then I have a 2 minus 1, that's a positive 1. All of that equals 0. And look where we're at again. We are in a position where we're ready to factor. We're ready to factor we're going to treat this like it was a quadratic. So A is equal to, I wonder if you guys can hear my dog barking in this video. A equals 2, B equals negative 3, and C equals 1. So we're looking for numbers that multiply to equal 2 and add to equal negative 3. So what times what equals 2? That when we add them together equals negative 3. That would be negative 1 and negative 2. But I have to remember to divide them by A. So negative 1 divided by A, negative 1/2. Sine of theta, negative 2 divided by 2 is negative 1. So we talked about, these are not the true factors of this equation, right? If I wanted the factors, I would move 2 to the coefficient, but we're solving this, so this is just going to save us a step. Just wanted to point that out. So I'm using zero product property. I take the sine of theta, first equation, minus 1/2, set that equal to 0, and sine of theta minus 1 has to equal 0. Solving it, I get sine of theta equals 1/2, sine of theta equals 1. This means, what are the angles on the unit circle that have a y coordinate? Equal to 1/2. Equal to 1/2. All right, so let's talk about that. I'm looking for a coordinate that has 1/2 in the y spot. So if there's a 1/2, the other half of my coordinate is square root of 3 over 2. Now, the sign of square root of 3 over 2, we could take a positive or a negative. But the sine of 1/2 has to be positive, right? That's what the equation said. So look at the pattern. What are the reference angles that use square root of 3 over 2, comma 1/2? Those are 30 degrees or pi over 6. Okay, so we want to use pi over 6 reference angles that qualify in the correct quadrants where the y coordinate is positive. That's quadrant 1 and quadrant 2. So theta is equal to pi over 6, that's in quadrant 1, pi over 6, and the 30-degree reference angle in quadrant 2, so I'm moving this angle into the quadrant 2, that would be 5 pi over 6. All right, so we've solved the first equation, the first factor. Now let's come over here. This one's a little easier. Sine of theta equals 1. So theta would be the inverse sine, the arc sine of 1, meaning we are looking for a coordinate that has a 1, a positive 1 in the y. We know if there's a 1 in the coordinate, 0 belongs there too. So which angle is at 0, 1? That is pi over 2. Pi over 2. And there are our answers. Oh, you can't see them. There they are. Pi over 6, 5 pi over 6, and pi over 2. Again, the interval that we were solving these on is from 0 to 2 pi, with 0 being included. So all of these are good. All of these solutions are good. We don't have to check them for discontinuities or undefined because these are sine, right? Sine is always defined. So these angles are good to go. All right. Let's check out number 13. So number 13 says negative cosine of theta plus the sine of theta equals 1. All right, and we're solving it again, 0 to 2 pi. I didn't write that on the previous ones, but you guys see it on your sheet. So this one is very different. We don't have our squareds in there. There's no Pythagorean identity I can use here. I'm going to have to do something different. Now, this process that I'm going to do, for the first step I'm going to do, may seem confusing to you, but the reason we have to create a new step, right, a new hint, none of the hints that we've talked about in class, is because I can't combine cosine and sine. They're not alike. I can't swap them out for any Pythagorean identities because they're not squared. It's so close to being a Pythagorean identity, but it's not quite. So I do have to create a new thing to do. I can't factor. There's no GCF. Like, what am I going to do here? So here's how you would approach this one. I'm going to do an operation to both sides. In the operation I'm going to square both sides. So I'm allowed to do this process as long as I do it correctly. You saw me include the parentheses on the left side. I'm squaring the side. I'm squaring the side. So think about what this means when I square it. Negative cosine of theta plus sine of theta squared means I'm multiplying it by itself. All right, and I'm going to set that equal to 1 squared, easy. It's 1. So now I'm going to distribute, right? I'm distributing, I'm foiling for those of you who learned that. Negative cosine of theta first gets multiplied by negative cosine of theta. A negative times a negative is a positive, right? It's a positive. So this is positive cosine squared. Then I'm going to take negative cosine of theta and I'm going to multiply it by positive sine of theta. A negative times a positive is a negative, right? It's a negative. And I have I'm going to stick them together. I can't simplify it like I did squared because they're different. So I'm going to say it's negative cosine theta, sine of theta. And now I'm going to do it again. Bloop. Sine of theta times negative cosine of theta is another negative cosine of theta, sine of theta. So notice I swapped the order here. That's okay. right? Multiplication is also commutative. So cosine times sine is the same as sine times cosine. And last but not least, we have sine of theta times positive sine of theta is a positive sine squared of theta. And all of that has to equal 1 squared. All right. I know it seems as if this is more difficult, but now we have terms that are alike, right? I have terms that are alike. I have negative cosine sine and another negative cosine sine. Together, that makes negative 2 cosine theta sine of theta. So that's those two. I meant to cross out the whole thing. That's those two things combined. I also have a positive cosine squared of theta and a positive sine squared of theta equal 1, right? So that's everything on the left side. I combined the stuff that I could. Okay? Now, watch this. At first, we thought we couldn't use Pythagorean identity on this one, but we can. But we're going to use it a different way. Look at this. Instead of taking them separately, look at cosine squared plus sine squared. What does the Pythagorean identity say cosine squared plus sine squared is equal to? 1. So we're swapping out the same way we did on 11 and 12. We're swapping things out, but we're doing it in a different way. Cosine squared plus sine squared equals 1 in the Pythagorean identity. So this whole big purple box becomes 1. So I have that 1, and it's a positive 1, right? It's positive. I still have negative cosine theta sine of theta plus 1 equals 1. Weird, right? So weird. So weird. What can we do now? What can we do now? We have numbers. So let's combine the numbers. What if I subtract 1 from both sides? I get negative 2 cosine theta sine theta equals 0. Huh. Very interesting. I have 1, 2, 3 things being multiplied together. Their product equals 0. The product of these factors equals 0. Well, I know something called the zero product property. The zero product property says I can take each factor and set them equal to 0. But really, this negative 2, because it's getting multiplied, let's just divide both sides. I'm allowed to do that. He's not inside a parenthesis. Everything's being multiplied, so I'm allowed to go like this. And now I have cosine times sine has to equal 0. I'm going to apply the zero product property. The cosine of theta has to equal 0. The sine of theta has to equal 0. The cosine of theta and the sine of theta has to equal 0. So theta would be any angle that had an x-coordinate of 0. Theta would be pi over 2 and 3 pi over 2. Theta would be, for this equation, any angle that has y equal to 0. So where are our y equals 0 equations? 0 radians, pi radians, and 2 pi radians. All right, so there's all of our solutions on the unit circle. Now, we know from the beginning that we needed to solve on 0 to 2 pi, where 2 pi is not included in our solution set. So he gets to go away. However, if we look back at the, I know you guys see the answers to these. Not all of these solutions are given in the answer set. Why not? And the reason is because when I performed my first step, this step that we haven't talked about yet, by squaring both sides, I'm creating a situation where I'm only looking at the positive values over here because I'm squaring it, so any negatives would turn into positives whenever I substitute them back in. So when we start a problem by squaring both sides, if that is, I guess not even start, if that's ever a step in math that we take to solve trig equations, we have to check our answers. Because squaring both sides does create an imbalance. It can create an imbalance in our equation. We needed to do it to move forward, but now we have set ourselves up where we have too many solutions, sometimes. Let me show you what I mean. So the original equation, we're going to check it on the original equation. Look back at the problem. It was negative cosine of theta plus sine of theta equals 1. So we need to check these 4 solutions. So we're going to check it 4 times. Okay? First check. We'll start with pi over 2. Okay? We want to know, does the cosine of pi, negative cosine of pi over 2 plus the sine of pi over 2, is that equal to 1? Is that equal to 1? So the cosine of pi over 2, cosine of pi over 2 is 0. Negative 0 is still just 0. So this becomes 0 plus the sine of pi over 2, the y-coordinate of pi over 2 is 1. And 0 plus 1 does, in fact, equal 1. So I am going to throw a circle around pi over 2. He passed the test, right? He checked out correctly. Let's move on to 3 pi over 2. Is the negative cosine of 3 pi over 2, I'm just plugging it in, plus the sine of 3 pi over 2 equal to 1. Let's see if this one works. The cosine of 3 pi over 2 is 0. The x-coordinate is 0, negative 0 is 0, plus. The sine of 3 pi over 2, the y-coordinate of 3 pi over 2 is negative 1. Does 0 plus negative 1 equal positive 1? No. This is a failure. This is a failure, so he can't be included in our solution set. So why is this happening? Why are we getting answers that aren't true? It's not that they're producing discontinuities or undefined values, but if you go back, remember what we did in our first step. We squared both sides, which means here we would have squared the quantity of 0 plus negative 1, which is negative 1. Squaring that does in fact equal positive 1. So by introducing the square to both sides, that's where we create a solution set, or solutions in our solution set that are actually illegal. So 3 pi over 2 is gone. Let's check the others. So I need to do the same thing with 0 and pi. Negative cosine of, that should be 0, plus the sine of 0, does that equal 1, right? So negative cosine of 0. The x-coordinate of 0 is 1. This says make it negative, so it's negative 1. The y-coordinate of 0 radians is 0. Does negative 1 equal positive 1? It sure doesn't. This is another failure. 0 is off the list. Last solution. So we crossed out 2 pi already, but we would do it again even if we forgot from our interval because 0 can't be included, so coterminal angles with 0 can't be included. Last but not least, the cosine of pi, the negative cosine of pi plus the sine of pi, does that equal 1? Well, the cosine of pi is negative 1. This says make it negative. Making a negative number negative means turn it into a positive. Plus the sine of pi, the y-coordinate of pi is 0. Is 1 plus 0 1? Yes. So here's our second solution. There's our second solution. All right, let's try number 14. And we're going to, where's my thing? There we go. We're going to do similar steps to what we just saw on number 13. Oh gosh, my dog wants in. Hold on. Go lay down. Go lay down. Okay. plus 3 cosine of theta plus 3 sine of theta. All right, so we're in a similar place as to where we were on number 13. What we're seeing is sines and cosines, but they're separate. We're not able to factor them. But we are at a little bit of an advantage here because on this problem, we do have some like terms, right? So it's not just a single sine and a single cosine term. We have multiples. For instance, look at this. Look at that. We have 3 sine of theta on both sides of the equal sign. So what if I move them together? What happens? Lucky for us, they both cancel. We have 0 equals the square root of 3 sine of theta plus 3 cosine of theta. All right, so this time we have 2 of these trig functions added together. It's equal to 0. Now, when something's equal to 0, we're allowed to move something to the other side. So I'm going to choose, it doesn't really matter. I don't know, I'll just move, I don't know, negative square root of 3 sine of theta. I moved it to the left. I'm going to keep 3 cosine of theta on the right. And now I'm going to apply the square to both sides. I can't substitute, I can't factor, I have no more like terms. I'm at a spot where I'm like, oh gosh, what am I going to do? Well, let's see if we can square both sides and get to the end. So now I'm just squaring a single term. So on number 13, we squared a binomial. So we had to FOIL or double distribute. And here I'm just multiplying negative root 3 sine of theta times itself. So I would say negative root 3 times negative root 3. That's a positive number. The square root of 3 times the square root of 3, square root of 9. I get 3. And then sine times sine is sine squared of theta. So this is what we get on the left side, equals. Now we're going to do the same thing to the right side. It's a little bit easier. 3 cosine theta times 3 cosine theta is 9 cosine squared of theta. So it may seem like, why are we doing this? Why are we squaring both sides? Well, we create this platform now where we can use that Pythagorean identity. So I have a sine squared and I have a cosine squared. I would really like to make those match. And I am in charge of how I am going to make those match. Meaning, I have cosine squared plus sine squared is equal to 1. Now, in the previous example, we solved for cosine squared and substituted that in. This time I'm going to solve for sine squared, because why not? Right? Didn't we do cosine squared? I think so, every time. I can't remember, you guys. My brain is mashed potatoes. I'm looking through my last work. Yeah, we solved for cosine squared. Okay, I'm not insane all the way. So let's solve this for sine squared by subtracting cosine squared to both sides. So sine squared equals 1 minus cosine squared. So where the sine squared is, let me get my other color. Where my sine squared is, so the 3 stays. It's part. I'm swapping out just sine squared for what we just solved it for. Okay, so I'm going to substitute those in. So we have 3 times. So because it's 2 terms, that's why you see me add these parentheses here. 3 times 1 minus cosine squared. That's what sine squared is equal to. Equals 9 cosine squared of theta. Look. We've got it to where it's matching now. We have only cosine squareds. It'd also be okay if there was just plain old cosines in there, but now we've made it match. I'm going to distribute. We have 3 minus 3 cosine squared of theta equals 9 cosine squared of theta. I have like terms. Who doesn't love a like term? I'm going to add 3 cosine squared of theta, because I like to keep my squared terms positive. 3 cosine squared of theta to both sides. This 3 drops down. 9 plus 3 is 12 cosine squareds of theta. Now I don't have to factor this one because all I have is one trig function. Just cosine. I know it's squared, but we've solved these before. I'm going to divide by 12. I get cosine squared of theta equals 3/12. 3/12 is 1/4. 1/4. I'm wondering if I made a mistake somewhere and I can't figure out where it is. I'm sure I will figure it out. It's awful that this has to be on video, but I feel like I made a mistake. I added, I have 12, I divided by 12, 3/12 is 1/4. Okay, let's keep going. Maybe I didn't, maybe I'm making this up. To solve, I take the square root, I take the square root, I have the cosine of theta is equal to, now I introduced the square root. I did that, so I have to put plus or minus here. I gotta remember that. Okay? Now I'm taking the square root of 1/4. We know how to do that. You separate it. Square root of 1 is 1. The square root of 4 is 2. So look how easy. We've whittled this down. The theta then is going to equal the inverse cosine of plus or minus 1/2. What angles on the unit circle have x coordinates of positive or negative 1, right? So we're looking for coordinates that have a 1/2, so we know the square root of 3/2 has to be the y coordinate. This pattern is 60-degree angles. That's pi over 3. Pi over 3. And because I'm allowed to be positive and negative, and I'm on an open interval from 0 to 2 pi, I'm going to pull every pi over 3 reference angle from all 4 quadrants. Pi over 3. 2 pi over 3. 5 pi over 3. Well, I skipped 4 pi over 3, but we'll do 4 pi over 3 and 5 pi over 3. I think you'll see why in a second. Now, we always have to check our answers when we square both sides. You should actually always check your answers no matter what, but especially when you're squaring both sides, or remember we talked about checking them when we're solving a discontinuous function. Okay, so the ones that have undefined answers. All right, so we need to check, and we always check on the original, right? We always check on the original. But really, guys, we can check on the original that we've simplified. I mean, we didn't change anything when we subtracted 3 sine theta to both sides, so we can check it on this one. It's safer to check it on the original just because, in case you made a mistake in your first step, but you don't want to check it on the squared one. That's why we're checking, is the squared version. So let's check on square root of 3 sine of theta plus 3 cosine of theta. That has to equal 0. So that's where we're going to check. And we're going to check 4 angles. 1, 2, 3, 4. First check. Is the square root of 3 times the sine of pi over 3 plus 3 times the cosine of pi over 3? We want to know, does that equal 0? All right, that's why it's helpful that we write our little coordinate here, because now we can easily see what the sine of theta is going to be. The sine of pi over 3 has a positive y coordinate. So for this one, we have the square root of 3 times the sine of pi over 3, which is another square root of 3 over 2, plus 3 times the cosine of pi over 3, which is 1/2. We want to know, does that equal 0? The square root of 3 over 1 is how we can write that, times the square root of 3 over 2. That means 9/2. I just lied to you. Square root of 9, which is 3/2. Is 3/2 plus another 3/2 equal to 0? No, it isn't, right? So this is a fail. Our first angle that we checked, pi over 3, already he's illegal. He doesn't balance. It's got to equal 0. Let's check the second one. The square root of 3 times the sine of 2 pi over 3 plus 3 times the cosine of 2 pi over 3. Does that equal 0? So again, we have the square root of 3 over 1. That's what this is. The sine of 2 pi over 3. So 2 pi over 3 is now in quadrant 2. The y coordinate is still positive. plus 3 times the cosine of 2 pi over 3. Well, if we've moved into quadrant 2, this is a negative 1/2. Does that equal 0? Square root of 3 times square root of 3 over 2 is 3/2 plus negative 3/2. 3/2 minus 3/2 is equal to 0. Bingo! We've got a solution. Let's check number 3. 4 pi over 3. Square root of 3 times the sine of 4 pi over 3 plus 3 times the cosine of 4 pi over 3. Does that equal 0? All right, square root of 3 over 1 times 4 pi over 3 is now in quadrant 3. Both of these coordinates are negative. So it's negative square root of 3 over 2 plus 3 times, I'm in quadrant 3, so it's again negative 1/2. Does that equal 0? This is a negative 3/2 plus another negative 3/2. Those aren't going to cancel. Not equal to 0. Bye-bye, 4 pi over 3. Finally, last but not least, 5 pi over 3. Square root of 3 times the sine of 5 pi over 3 plus 3 times the cosine of 5 pi over 3. Does that equal 0? Square root of 3 over 1 times, we are in quadrant 4. Quadrant 4 for 5 pi over 3. Quadrant 4, y coordinate is negative. In quadrant 4, the x coordinate is positive. Does that equal 0? Does negative 3/2 plus 3/2 equal 0? Yes. I didn't put an x there. Yes. 2 pi over 3, 5 pi over 3 are the answers. If you scroll to check on your answer sheet, I bet that those are the ones that are there. So you have to be careful when you're squaring both sides. You've got to check your answers. Because again, what we're doing by creating this scenario where we square both sides, we're looking at turning everything into a positive. So all of these times where we had a cancellation with a positive negative wouldn't have happened. It wouldn't have happened. So that's why we have to check. So hopefully you've still tuned in. You're still here with me. If not, I totally get it. Maybe a few years down the road when you need this video, when you're in college or whatever, you're in your IB math course, if you're part of the magnet program, you'll come back and visit. Bye for now.